Now at the new prices, the expenditures here look like this. To get the consumer at these new prices back to the original indifference curve, that is with utility U, we could have them face the new prices but take away some income. How much would we have to take away? Well, we have to shift this thing in a parallel way so it was now tangent to the old utility curve. And this distance here is going to be equal to this compensating variation divided by the price of good Z, which is 1 in this case. Okay. Is the graphical construction clear? So we lower a price. People like lower prices. The lower price makes them better off. We want to keep their utility constant, though. So at the same time we lower the price for the light they're paying, we take away some income to get them back to the original level of utility. And that tells us, that's one way of measuring the value of that price reduction to the consumer. So it's the amount of money you can take away from them that would make them indifferent between having a lower price or the higher price. Let's go ahead and work that out in this example. Are there questions before I start? Yes. Eric. Oh, sure. Yeah, you can do it on the other axis too. Here you need to remember we're messing around with the price of L, though, so it's a little bit. We usually want compensating variation to wind up being measured in dollars or some unit of account like that. And here PZ is 1, so it has a nice simple interpretation. But you could say you could do it the other way around and say, well, how much light do I have to take away from this guy in order to make a difference to them? Okay, other questions? All right, let me go ahead and tackle this problem. So we're going to try to figure out the value of introducing LEDs to consumers, and with the resulting decrease in price from $9 per megalumen hour to $0.44 per megalumen hour. So we have a couple things we need to do here. First of all, we need to get an expression for the. If we want to come up with a number, we need an expression for the expenditure function. Anyone have a candidate? How would you solve that if we're going to do that from scratch? How would you compute the expenditure function? Well, there's a way to get it via indirect utility function, but that's not the most direct. Yes. Sorry, say again? We use the Hicksian demand. How do we get the Hicksian demand? We minimize expenditures. That's what this is. So if we wanted to solve a general expenditure function over two goods, we minimize expenditures subject to the requirement of making our utility a minimum level of U. So subject to U of x1, x2 being greater than or equal to this level of utility U that we're fixing here. Okay. So this is, remember, you can see the dual problem or the expenditure minimization problem. The solution to this minimization problem tells us what the minimum expenditures the consumer needs to make in order to achieve level of utility U are. And so it's this function that we're after in this case. Okay. Let me do a couple things here. So we need to compute two things. One thing is this function of prices and utility. And we can work that out by solving this problem. We know what expenditures are. We have prices. We've got a utility function. We're assuming that's equal to, I'm going to write down this thing. We've got this utility function we can use. So we're in a position to calculate the expenditure function. Something we don't have yet. So even after we get the expenditure function, there's still something we're missing. Anyone know what it is? Do you want to go about plugging in some numbers here to get a compensating variation? What else do we need to know aside from the expenditure function? Yes, Scott. Yeah, that's right. So Scott's got it. Once we the things we don't know up here include right now the function. We've got the prices both before and after, but we don't have a level of utility yet. Okay, so that's an important piece of the puzzle. How can we get the level of utility? So again, be a level of utility for the average global consumer. Okay, so we'll go back to the utility function. Actually, here, if we knew what demands, we do. We can figure out what demands for light and other goods are. We can plug those into the direct utility function. We can also use the indirect utility function and sort of save ourselves a step. So let's go ahead and do that first. So we want to figure out what the level of U is for the average consumer. So in this case, we've got U is going to be equal to the indirect utility function. It's a function of prices right now, so this will be $9 later on, and of income. I guess I usually write this with Y first. Okay, so that thing. What's the given the direct utility function we've got? Do we know what the indirect utility function is? If we don't know, how would you compute it? This is equal to the solution to the consumer's utility maximization problem, subject to the budget constraint. Okay, so that's that. With this particular utility function, though, you guys have done this math a bunch of times. You don't really need to do it again. You can just consult your notes and maybe substitute it for right here or something there like that. What's V of P? What's the indirect utility function for V's? It corresponds to this utility function. Okay, so I hear some things I'd like to hear. So in this case, this is equal to the log of Y. What else? Well, close. Minus, we do it. Yeah, minus alpha times the log of P. This is the price of light. What else? Okay, good. So there should be a minus 1 minus alpha log of P. I guess I was calling this PZ before. But this is equal to 1. We take the log of 1, it's going to be equal to 0. So this whole thing is equal to 0. So we're left with this nice expression here. I should say that there's also typically some constant A kicking around here, which I'm going to ignore right now. It'll tend to follow this thing. Okay, so we've got a function for the indirect utility function, which is log of Y minus alpha log P. This is the piece we're interested in. Okay, so we can use that for indirect utility function. Yeah, Eric. PZ is 1, and the log of 1 is 0. Is it clear? Okay, so log of Y minus alpha log P is an expression for the indirect utility function. We've got numbers for these things. So the log of per capita income here, what did we say it was? 8571. So this U is equal to log of 8571 minus 0.0072 times log of P, which is 9 to begin with, recall. And what's that equal to? Again, someone with a calculator. I'm using I'm using u right in this context to mean a number, the number of utils that the consumer gets if they have an income of y, the face price is p, and we plug that into the indirect utility function v. Okay. Okay. So we have a claim. Let's put that here. So we get that u is approximately equal to 3.93 in this case. This is before the price change. Right? This is the utility that the consumer has when they face prices of 9 per megalumen hour and have this income of 571 per year. Yes. Oh, we better reconcile that. Okay. Oh, yeah. So I do want to. Thank you. Yeah. So when I write log like this, I mean natural log. Yeah, thanks. Actually, as long as you're consistent about whether you use natural log or log base 10, it won't cause a problem. But let's stick with the natural log. Okay. So I'm sorry. So what was it? There we go. Okay. All right. So that's the value of u. I'm going to assert that we can write the expenditure function here like this. We'll get e to the u times p to the alpha, and that's it for this thing. In the more general form, we have the other price kicking around here, but again, that's 1. So it would be the other price raised to the 1 minus alpha, so that thing's going to cancel out. So our expenditure function here just takes this very simple form. Okay. All right, does everyone, does that look totally mysterious? Yeah, I kick out the when we get these constants like this, we can always redefine the utility function, so we just subtract the constant off. So yeah, I need to be a little bit careful about being consistent. I'm going to ignore the constant. Yes. How do I get the expenditure function? In this case, memory, because you'll recall that if you think back a couple lectures, I said that when we had, where should I write this? Put it up here. So I solved the problem of expenditure minimization using a slightly more general utility function a couple lectures ago, and I said that if we have u of x1, x2 through xn, then equal to this, the sum over alpha I log of xi plus phi, so that was the utility function I used, sum it over I equal 1 to n. Then I said that we get an expenditure function, e of p u, which looked like a constant a, again, we're going to ignore that one, e raised to the u times, I'll write it this way, p1, the alpha 1, sorry, this is assuming also that the sum of the alphas is equal to 1. So we get an expenditure function that involves p1 to the alpha 1, p2 to the alpha 2, pn to the alpha n, minus the sum I equal 1 to n of pi phi. Okay, so that was a general result that we got previously. The example we got now is just a special case of this, where alpha 1 is equal to alpha 2 is equal to 1 minus alpha, all the other alphas are 0, p's are all equal to 0, and I'm asserting that we can ignore the constant a, so that gives us the result here, just the e to the u times p raised to the alpha. Okay. Yes, Scott? No, it's true. This is true for this utility function, but notice, I mean, this one's a more general version of the one we've got for the light case. We get the light case by setting the phi's all equal to, well, setting n equal to 2, setting all the phi's equal to 0, setting alpha 1 equal to alpha, and setting alpha 2 equal to 1 minus alpha. So the light case here is just a special case of this more general utility function. Yes, go ahead. In the thing up here, the phi's are all 0. P to the 1 minus alpha would be here, but remember p is equal to 1. Okay. Yes. So I've given examples that look kind of like this, where I was subtracting something, and I call that a subsistence level. Here you can call it a minus subsistence level if you'd like, or I mean, if you change the sign, you just change the value of the parameter. It's not, it doesn't change anything except the interpretation of the parameter. Yeah. Oh, if you wanted to interpret it, you might say that you start off with some natural level of the good that can't be taken away from you. Yes. Subsidy. Yeah, I prefer not to call it a subsidy because that usually refers to something that affects prices. Yeah, it's more like a grant. Yeah. Okay, so anyway, so in this case, we're going to get an expenditure function that looks like this. You guys know how to solve this thing by solving the expenditure minimization problem. For this problem, we get this nice simple formula. Yes? You can do two things. One thing you can do, this is always an option, is if you're given a direct utility function like this one, you can go off and solve the expenditure minimization problem, which do I still have that written down? No, I don't. But anyway, you can solve the expenditure minimization problem. That'll always work. But you might already know the answer from some other source. One way you might know the answer is by having solved the problem for a fairly general utility function like this. And in the current case, we've solved this already. You got it in your notes. And so if you can see that the utility function in the example is a special case of this more general one, you can go ahead and say, well, we know the expenditure function in general is this, and then just apply, say, and so there's only two goods, so all these p's except the first two don't matter, so on. Yes. Yeah, that pesky a. So the constant a is something. In this case, I think it actually takes the form. Don't quote me on this because I might be misremembering. But I think a takes the form here of some. No, it takes the form of e to the sum of alpha I times the log of alpha I, and I guess this should be. So I think that's what it looks like here for here. This is what this thing will be. I think that's based on recollection rather than calculation right now. Because this constant doesn't, it's a constant. It only depends on these alphas, which we're taking as fixed. So we can sort of get rid of it without causing too much trouble for most of our calculations. Okay, so back to this calculation. We've got an expenditure function, which is e to the u times p to the alpha. For this application, we've got some numbers we can plug in here. We've got e raised to the 9.04. And we've got p to the alpha is 9 raised to the 0.0072, approximately. And so somebody do that calculation for me, please. Do I hear an answer? Okay, so this e to the, this is a nice point. So this e to the u, remember that u depended largely on being the log of 8571. So when we raise this whole thing to the when we exponentiate this thing, we're going to get back something close to that. So we're going to have e, we're going to have, I'm sorry, what was the figure? Okay, 66? Okay, we've done some rounding here, so this is going to be approximate anyway. So that, and then 9 to the 0.0072? That was the whole thing, okay. Oh yeah, so this part actually should be exactly 85. Okay, let's do it in pieces. What's e to the 9.04? It sounds like there might be some questions, though, or some observations here before we keep going. Yes, Wes. Okay, so yes, my plan is now to go back to this calculation of compensating variation. And so recall that our compensating variation was just equal to e of pu minus e of p prime u. And we just said that this is equal to 8571. It's the expenditures given the current prices that give us this level of utility u. Okay, now here's the more interesting part, minus this thing, which is equal to e to the u, all times a price of 0.44 now, and the same level, I'm sorry, what am I doing here? It should be 0.44 raised to the 0.0072. So this is equal to e to the u times p to the alpha. Yes, Hillary. Oh. Okay. I'll switch around to be consistent. It changes the interpretation, whether or not you're compensating people for a price change. Or, so yeah, no, I should it this way. Pardon me. So we'll make it equal to this minus 8571. Thank you. Okay. Now we have a calculation for u. This is where we'll use this, which is 9.04. So e to the 9.04. So remember the key here. This is really important. So the key to compensating variation is we're trying to keep utility constant. So it's how much income do we take away from the consumer to make them as well off as they were before the price change. That's compensating variation. And so we want to use the same u. Absolutely. Here and here, these are the same. It's only prices that are different in this calculation. So e to the u is e to the 9.04. The price is 0.44 raised to the alpha. So somebody at the calculator can help me. So just this part, 0.44 to the 0.0072. 994. Okay. And then so we multiply this times this, and what do we get? 8387. Oops, sorry, I shouldn't do this. I shouldn't. This is equal to this, so I don't want to lose my 8571. And so this difference, I can almost do it in my head, but I'm not going to. Let's see. Is that right, 184? Minus 184. Okay, so if we've got this right, this tells us that rather than a price decrease per lumen of $9 to 0.44 cents, a consumer would be indifferent between having that price decrease or having $184 taken away from them. So that's the measure of welfare associated with this proposed price decrease of light. Yes? Yeah, it's because this number really should be 8571, this is a rounding error, so which gives us a number which is slightly off. It's a good question. Other questions? Hillary? You can, yeah, that's right. So having lower prices for light makes them better off. It makes them just as well off as having the new prices, but also taking away $184. Yes. Very good. Yeah. So it'll be that's exactly right. Let me draw that picture. Let me try to draw that picture for you. So here's the indifference curve associated with this level of utility u, which we said is equal to 9.04. And we had some old prices. This is for Z. This is for light. We had some old prices that people are consuming here. We lowered prices